No homework. Your homework, you have homework. I haven't written it down. It's study.
Yeah.
Everything. From the beginning of everything to right now, everything. Because this final is going to be a doozy. Because it's a take-home final. And it's going to be comprehensive. Although, I mean, if you study, it shouldn't be too bad. So, but we'll go over it on Thursday, and you know, we'll go over it. So study, and study. What's that?
We just have 2 classes after today, right?
Just one. We're just
we're
gonna
not doing anything next week.
No, because it's Monday, and Monday's Memorial Day.
Oh, true.
So and so that's why we're gonna wrap up with something more advanced today. And it may or may not show up in the final. I mean, though everything we're talking about is, you know, well, of course everything's fair game, but it's in the same line as everything else. I might give you one on something we do today. Again, it's a take-home final, so you'll have access to all the videos.
Yeah.
So, good luck. Okay, so we've talked about initial value problems. Right, that's where you have a differential equation with some initial condition, because of course the solution to a differential equation is infinitely many solutions. Infinitely many functions satisfy a differential equation. And so we have to pin it down by saying, okay, it has to go through this point. But if you have a second or higher order differential equation, you'll notice here we have the function itself, its first derivative, and its second derivative. We could equivalently write it like this if we wanted to. I don't want to write it like that. I want to write it like this. Okay? It's not enough to just have one initial condition. We could say at y0, what did I want to use? We're going to say at y0 it goes through 1. We have to have more because there are more unknowns. When you just have a first order differential equation, that's enough. You say, well, the original function has to go through there. Now that you have a second order, there's more degrees of freedom here. And we have to pin it down even more. And so an initial value problem with a second order differential equation is also going to have to give you one more bit of information. And usually, that's information about the first derivative. So you'll notice when you have a differential equation with one derivative, then the initial value problem is the second lowest thing, right? Like the highest order is the first derivative, the second one down is the function itself. When you have a second order differential equation, you usually are specified with this guy and with the first derivative. And in this case, this is going to be our initial value problem right here. Now it is possible to, if you have 2 points, so this is 1 point, the point 0, 1. You could also, if you had, say, at 1 it's, say, 2, that could be enough to do it. Because that's 2 bits of information, and as you'll see, that would be enough to solve this problem. But it's usually given like this. So you know the initial position of your thing, whatever it is, and the initial, in this case, velocity. The velocity at time 0 would be there. Okay, so here we go. We've seen something almost exactly like this before. And when I introduced this, I said, believe me, the solution to this thing has this form. We're going to use t. Y of t is equal to some constant times e to some parameter times t. I said, trust me, this is a solution to this. And I said, let me show you that it is. We're going to take the derivatives here. So let's take the first derivative, and what do we get? Y prime is equal to what?
CR e to RT.
Yeah, because the constant comes along for the right. Take the derivative of e to the stuff. It's just e to the stuff. Take the derivative of the inside. The variable is t, so r times t, yes, the r pops out. Okay, now what about y double prime?
That would be CR squared e to RT.
Yeah, it's the same. That's just because r is just a constant. The derivative of that is itself. Then we multiply by the derivative of the inside stuff. The r pops out. There's an r there, so we get 2 r's on the outside. There we go. Right. Now, here's the thing. Not every r is going to work here. right? But we could go ahead and say, now let's just think about, okay, hold up. When you take a course in differential equations, what they do is they'll just say, if your differential equation looks like this, use this. If your differential equation looks like this, use this. And there's not much theory behind it. If you want the theory behind it, take a course in analysis. Take many courses in analysis. And you'll get all the theory you could possibly want. A course in differential equations is pretty much an applied math course. It's like, how can we use this to our benefit? And that this is what you're going to learn. And really what this comes from is, most likely what happened is somebody encountered this and said, I don't know, man, what kind of function would do that? Well, it would have to be a function that when you take the derivative of it, it gives you the same kind of thing. E is a kind of function that gives you the same kind of thing as itself. In order to make it, when you subtract it off, it goes to 0. So maybe it's E, and then you try it, and you find, let's see what we find. Let's just plug this in. Y double prime is this, so I'm going to plug him in right here. CR squared e to the RT minus, plug in y prime right here, we have CR e to the RT minus 2 times the original thing y, which is C e to the RT, and we say that that thing has to be equal to 0. Yeah. So you kind of stare at it and you go, well, I don't factor out common factors. I notice we have a RT, e to RT, e to the RT in each one. We also have a C in each one. So we're going to factor out the C and the e to the RT. And before I do that, I'm just going to notice something. I'm going to have some thing here. C, unless it's 0, in which case it's the most boring function ever. We call that the trivial solution, because yes, 0 and the derivative of 0, which is still 0, and the derivative of 0, which is still 0, does satisfy this equation. Although it doesn't satisfy this.
Oh.
Yeah, so that wouldn't work. But it would be without this, it would be a trivial solution to this, and we don't care about that. But now we could say, okay, so unless C is 0, there's no number you could plug in here that's going to make this part equal to 0. And so in other words, you have A times B equals 0. One of those bad boys has to be 0. If A can't be 0, which that cannot be 0, then it's going to have to be the case that whatever's left here is going to have to be 0. Right?
Yeah.
Okay. And so again, I think we've done exactly this. It might not have been exactly this equation, but we've done this before. The only thing that's left is an r squared minus r minus 2. And now you know what to do. What do we do with this?
Factor.
We can factor this guy. So we're going to factor him down, and what do we get? There should be an r and an r.
Minus 2 and plus 1.
And a plus 1. I think you're right. Let's double check. First gives you r squared. Outer positive r. Minus 2r gives you minus 1r. Yes. Negative 2 and 1 give you negative 2. Yes. Okay. So now we found bounds on r. We found 2 possibilities for r that will work in this equation. And what are they? R equals what?
2 and -1.
R equals 2 or r equals negative 1. Okay. So now it looks like we're getting 2 possible general solutions here. This should make this if you weren't expecting this, it should come as no surprise, even if you weren't expecting it, that you have more degrees of freedom here, right? Your differential equation involves more stuff, so there are more possibilities of things that could work.
That's why we need 2 things.
So what this looks like is, it looks like if your function it looks like we have 2 possibilities for a general solution. One of them, I'm going to call it y1, is going to be some constant, and let's call it c1. E to the, and we're going to pick either one of these. Let's do the 2 since it's on the left hand side. 2t. That should be a solution, and not just that one, any one of those. So there's infinitely many possibilities here, which should be a solution to this differential equation. Another one that works, I'm going to call it C2, because it could be anything, e to the negative 1 times t, or how about just negative t? Okay. Now each one of those individually should be a solution to this differential equation. And I mean, we could try it. Let's try. Why not? Let's just try it with one of them. Let's try y1. So I'm going to need y1, which we have, y1 prime, which is going to be c1, whatever it happens to be, 2 e to the 2t, and then y1 double prime, which c1 stays put, the 2, and now another 2 comes out, so how about 4 e to the 2t. I'm just going to plug it in. Y double prime is c1, 4 e to the 2t, minus y1 prime is this guy, c1, 2 e to the 2t, and then minus 2 times the original one, which is c1 e to the 2t. Now let's just see, how about we pull out our c1, and how about we also pull out the e to the 2t. What's left over, I guess, c1 minus 2c1. Oh no, we pulled out the c1. I'm sorry. So 4. Man, what am I doing? 4. Okay, we pulled those out. We have a 2. We pulled those out, and we have a 2.
Yeah.
Does that work? Yeah, that actually it does work. It satisfies the original differential equation. The same thing's going to happen if you do this. So that's cool. But here's the thing about differential equations, is if you have, and I'm sorry, I meant to look into this before I said it, because I don't want to say something that might not be true in every case. But I can tell you it's absolutely 100% true that if you have we call this a linear differential equation, in the sense that it's some constant times, or how about some constant times y plus some constant times y primes plus some constant times y whatever, and on and on and on until you have some constant times y to the nth derivative equals something. Maybe it's 0, maybe it's not, we'll just say it's 0. If your differential equation looks like that, then it is 100% certain that any linear combination of these guys, that is, you add those together, it will also be a solution to this differential equation. We could prove that. I don't want to, because we have bigger fish to fry right now. It just happens to be true. I'm not sure if it's true in general, because when you start doing nonlinear stuff, like if you were to multiply 2 of these guys together, like if your thing looked like this, let's say 7 plus y, third derivative equals 0. I'm not 100% sure that what I just said is still true. I'm pretty sure it is, though. I'm pretty sure it is. But it's so don't quote me on that, but as long as your differential equation looks like this, I could tell you with 100% certainty that if this thing is a solution to it, and this thing is a solution to that, then so is its sum. The sum of these guys is also a solution to the differential equation. And we're just going to see that in this case. I'm going to go ahead and explicitly write it out. I'm saying that the general solution to this thing is the sum of these things. The general solution looks like this. That's my claim. That this thing is the general solution to that. And you'll never see a proof in a class on differential equations that this is the general solution. It turns out to be true. Because my question when I was taking this class was like, well, how do you know that you can't go about some other means, come up with something that looks completely different and it's also a general solution? It turns out you have to take some pretty high-level analysis, that if you have a general solution that looks like this, and a general solution that looks like anything else in the world, maybe it looks like some kind of polynomial,
Goes on.
and maybe like this, maybe it looks something like this, right? It turns out that those two things will be equivalent.
Okay.
Right, and yeah, and so if you have it, it looks like anything else. Let's say some weird function g of t. It turns out that they are equivalent. That this is just a fancy way of writing one or the other, and so, but you need some really high level analysis to prove that. We're not going to do that. We're just going to do this case right here. This differential equation. This initial value problem. Now, my claim was that this plus this also solves this differential equation. Well, let's check it. Let's see. What's y prime of t? 2c1 e to the 2t.
Minus C2.
Because the minus is going to come out. Minus c2 e to the minus t. So what's the second derivative of this guy?
4c to the 2t plus
4c1
yeah,
e to the 2t
plus c2.
plus c2 e to the minus t. Now let's just check it. We're going to take these guys, plug it into the original differential equation, and we get 4c1, we're going to run out of room here. Whatever, who cares? E to the 2t plus c2 e to the minus t. That's the first part. Minus y prime, which is c1 e to the 2t minus c2 e to the minus t minus 2 times the original thing, c1 e to the 2t plus c2 e to the minus t. And we want to know, is that indeed equal to 0? I'm going to do this fast and furious. I'm going to go ahead and combine this part, and this part. And I'm going to get 4c1 e to the 2t minus 2c1 e to the 2t minus another 2c1 e to the 2t minus 2c1 e to the 2t. Okay, that's those parts. Now let's get this one, and this one together. We'll have plus c2 e to the minus t. The minus comes through and hits this minus, right? Minus to give me a plus c2 e to the minus t. Minus comes through, hits the plus, and gives me minus 2 c2 e to the minus t.
Yep.
Is that equal to 0? And we actually don't have to factor anything out because they all happen to work out, right? 4 c1s of this thing minus 2 c1s of that thing minus 2 c1s of that thing. Well, that's the same. Or I could be really explicit here and just do what we've been doing. Pull it out. Pull out the c1, comes out of each one. Pull out the 2t, e to the 2t, e to the 2t. What's left? 4, a minus 2, and another minus 2. That's nice. Pull this out here. We have a c2 and an e to the minus t. c2 e to the minus t. So that leaves me with a 1 plus, pulled all of that out, another 1, pull all of that out, that's a minus 2. That's 0. That's 0. So it is indeed 0. Now you kind of see what I mean. If everything is a linear combination, some constant times a solution, some constant time, or sorry, everything here is some constant times a solution, some constant times a solution. You add those together, you have a constant times a solution, constant times a solution. Well, when you go and plug that into something that's linear, which is again, constant times solution, constant times solution, constant times solution, you'll do a bunch of flip-flopping and rearranging, but in each case, this thing solved that thing.
Yeah.
This thing solved it also. So you'll be able to just pull all of your constants that you've multiplied in and rearrange, and everything should work out. So we've not proved that a linear combination of solutions is a solution, but I think you see how we could prove it in general, because it works so well in this case. Be a little creative. You could do this in general if you write out a(n) y, the nth derivative, plus a(n minus 1) y to the n minus 1th derivative, and so on down to y a1 y prime minus a0 y. It's just, why would we go through that? Obviously, this is how it works. So, okay, so second order linear differential equation initial value problem has this type of form. There are two constants to be determined. And if you have two unknowns, how many points do you need?
Two.
Okay, and so this is kind of how this works. This is why this is this way. So let's actually solve this one, okay? We found that our general solution is indeed a family of functions, kind of doubly infinite in a sense, right? Like C1 could be any real number, and C2 could be any real number. But let's see, we know a couple things about this. We know that we needed the other one. We know that when I plug in a 0, I need to get out a 1. And when I take the derivative of this thing, which, one more time, what is the derivative of this thing?
2c1 e to the 2t minus
2c1 e to the 2t minus c2 e to the minus t. Okay, I know that when I plug a 0 into this one, I get out a 1. So let's plug a 0 into that one. We get c1 e to the 0 is what? 1. So do I need to write it there?
No.
No. When I plug a 0 into here, I get e to the 0, which is 1. So that's just plus c2. Okay. Plug in. This says that the derivative, when you plug a 0 into the derivative, you get out a 0. So I plug a 0 into here, I get a big fat 1. So that gives me a 2c1 minus c2 times plug in a 0, I get a 1 minus 2c2. And we have a system of equations. And you could use your favorite method to figure this out.
Just solve for one and then plug it into the other one.
We could add that. It's actually, you know, I did this one way. I solved for one. It'll actually be easier to just add these together. Add these equations together, and I get 3c1s plus 0 equals 1.
Yeah,
So that c1 equals a third.
Which means it's 2/3.
And so yeah, the other one should be 2/3. Let's just make sure of that. Let's choose either one of these. I'll choose this one. Plug c1 in here, I get 1/3 plus c2 equals 1. So c2 equals 1 minus a third. So c2 is equal to 2/3. There we go. And so our particular solution, so this is the general solution. But if we want the general solution which goes through these points, or which you could say goes through 1 when time is equal to 0, and has velocity 0 when time equals 0, then the function that we want is y of t equals c1 was 1/3 e to the 2t plus c2 is 2/3 e to the minus t. That would be the particular solution, which has this. So we could say, I know this function, whatever it does, when time is 0, it goes through at 1, and its velocity there, or its slope there, is 0. So it's flat there, and then I don't know what it does. I guess this one's going to blow up eventually, so it's probably going to go up. And then, I don't know, he's going to take over and do something and go back up. I don't know. Who cares? That's not really the point. The point is, that's the particular solution for this initial value problem. make sure I didn't mess that up because we might be seeing this one again. 2/3 minus t. Yes. 1/3, 1/3, and 2t. Yes. Okay? Do you think that if that were to, I don't know, pop up later, you'd recognize it?
Yeah.
Okay. Alright. Okay. Now for something completely different. Oh, actually, before we do that, I want to leave him up there and leave him up here. Just want to say that this guess and check method is one of the methods you'll learn. There are other methods of dealing with this. And one thing you'll notice that we can't do, that we could do with the others, is you get the derivative by itself and you want to make a slope field. Cool. Uh-oh. So you can't do the slope field method with that. If it were that, you could easily make a slope field and your life would be easy. But yikes, there is a way of turning this into a matrix problem. Yeah, and in general, if you have, I don't care how many derivatives, if it's linear, that is constant times a function, constant times a function, constant times a function, then you could turn one of these into a matrix problem. And given this is what's going to pop out of it. So that's pretty cool. But we're not taking a course in differential equations. So now for something completely different. This is a function. This thing right here is a function of some variable. What variable? T. Sure about that? Let's compute it and figure this out. So, what's the antiderivative of this thing here?
E to the negative s.
Minus st, but
Times. Wait.
yeah, times something. Here's a hint.
Negative 1 over s, or
Yeah, 1 over, how
Yeah.
about negative s, or negative 1 over s. And let's just check it, Take the derivative of this, you get that thing back, then you multiply by what?
s.
Negative s.
Yeah.
And if you multiply by negative s, does that
You
kill
just-
all of
yeah.
that and make it go away? Okay, good. So now we need to take this thing and evaluate it at its endpoints. And this is why it's not a function of t. Now, of course, that means that we're going to evaluate it at n and then take a limit as n goes to infinity. So we're going to take the limit as n goes to infinity of negative 1 over s e to the minus st. Minus s n. There we go. Right?
Yeah.
Right, I just plug that into that function. T is the variable in that function, so I plug him in. Okay. Minus off negative 1 over s e to the minus s. Now I'm plugging in a 0 for t. But, so that's 0, which is just 1. Okay, so I could just get rid of that. Okay, cool. What's the limit here?
As it'll go to 0.
It should, as long as s is positive, right? If
Oh.
s is a positive number, so now, I mean, it might blow up. If s were a negative number, then you'd have negative, which would be positive, and then this would blow up. But if we say, whoa, we got to this point, we go, wait a minute, that would be bad. So what do we need to do so that it doesn't blow up? Well, if s is positive, then negative s is negative, and then e to the negative sn looks like this. And so now, if you were to do that, then what does this limit turn out to be?
0.
big fat 0 minus a minus is plus 1 over s. So this thing is a function of what?
S.
S. And do you believe that it's a function?
Yeah.
I could plug in any value of s as long as it's bigger than 0, and it's perfectly well defined, right?
Yeah.
As long as s is bigger than 0. So I'll go ahead and put that up
And
there.
that's what the area under that is.
Then the area under this thing would be 1 over s. You could think about it that way. Okay, okay. That was something completely different. And just notice, right, whenever you have whatever this d, whatever, this is your variable of integration here. And if you have a definite integral, you're integrating that where from t goes from 0 up to infinity, then the t disappears. All that's left is the s. Only the s remains here, right? The t's are gone. I could, in fact, I could have, at the very beginning, replaced this with anything. I could have said, how about big capital A? Is that still true?
Yes.
Yeah, it didn't change anything. What if I called it x? Yeah, you see, and this is why we call it a dummy variable. Because when you take the definite integral, whatever you called the thing, we called it t, yes, you end up with a function of t here, and we're treating s like some kind of constant. But then once you evaluate it, the t's go away, because you plugged in actual values for them. Then your s, whatever it happened to be, and this is, you hear how I said that? Whatever it happened to be, well, that's what a variable is, right? We didn't specify, when s is 5, or s is a constant. I never said s was a constant. We're going to treat it like a constant, because as far as t is concerned, it's a constant. But, yeah, this is called an integral transform. And what that is some function of some variable, we'll call it s, and it's written over some definite interval. It might be infinite, okay? So alpha and beta may be plus or minus infinity. That's okay. They could, like in this case, alpha happened to be 0 and beta happened to be infinity. You could go from negative infinity to infinity, or you could go from negative infinity to 7 if you want. That's perfectly fine. The integral transform has this form. Some function of s and t times a function of t dt. So you have this thing here, whatever function this happens to be, and in this case, that was my k. My k is e to the st, so there's 2 input variables there. F of t, I guess, happens to be 1 in this case. I didn't use that for anything. But this here is called the kernel, like a seed or something. A kernel. It's called the kernel of the transformation. Okay? And what this does is this transforms f into another function. So we are and often we use t here to think about this as like time domain, or if we're dealing with, oftentimes with differential equations, our input value is t because differential equations often use time as the input variable. But you could take a function, and depending on what you choose here, turn your function of your variable t into a function of a new variable s, and that could have some kind, it may or may not have some kind of physical significance. Okay. Okay. So that's in general here. Let's not forget this. Let's not forget that when I take the integral from 0 to infinity of e to the minus st dt, we get 1 over s, just so long as s is positive. Let's not forget that. We'll come back to him in a minute. Okay. So that's, in general, if you do that, you multiply a function by another function and you integrate with those things that I just did. It's called an integral transform. Now, let f of t be defined on 0 up to infinity. So in other words, well, what I mean by that is that for all positive t's, right, we can plug in any one of those guys. Anything from 0 up to positive infinity. If f is nice, we'll get back to what nice means in a minute. It'll be much easier if we just do some things first and then say, oh, that's what you mean by nice. We'll just say if t is nice, if it's a nice function, then the Laplace transform of f is given by, we usually use this big curly L for Laplace of f, which is a function of t. I will drop that of t as we start doing these. It's defined as the integral from 0 to infinity e to the minus st f of t dt. Just so long that this thing converges. When does it converge? It will converge if it's nice. Okay, we'll get there, we'll get there. It's like, because you're taking an improper integral going to infinity. There's no guarantee that you could just plug in any old function and it's going to converge. If it does converge, then that function is nice. So, yeah, okay. This is the thing. So, okay. We'll get back to what nice means in a second. Let's do one of these. Let's say, let's let f of t equal e to the a t, where a is some real number. Maybe it's e to the 5t, or e to the negative t. Okay? Then the Laplace transform of it, let's just compute this guy. The Laplace transform of f is the integral from 0 to infinity, e to the minus st, and now instead of f of t, I'm just going to replace it with e to the at dt. Okay, okay. How could we simplify this?
It's e to the at minus st.
There you go. At minus st, which I think we could simplify a little bit more by pulling out a t. And then we'll treat this as a constant. Because as far as this integral is concerned, a and s aren't moving. Whatever they are, we're just going to pretend they're constants. And so we have a minus s t dt. Okay. Everybody got that?
Yeah.
What is that antiderivative? Let's figure it out.
So it's
It's
1
the stuff.
over...
Yeah, hold on. So it's this, it's going to be this stuff, a minus st, and then what?
times 1 over a minus
1
s.
over a minus s. There we go. Now let's double check it and see. Take the derivative of this, you get that. Inside, then we multiply t, t goes away, the a, the s come out, a minus s, yes, okay, we're back to where we start. Now we're gonna go, okay, we'll take a limit and we'll evaluate here. So we're gonna take a limit as n goes to infinity of 1 over a minus s e to the a minus s n minus 1 over a minus s. Now, e to the a minus s, and I'm going to plug in a 0, is the same thing as e to the 0, which is a big fat 1, so it's just 1. Now,
So s has to be bigger than a.
there you go, right? Because we're thinking, okay, can I do this? Well, it's going to blow up if a minus s is a positive number. So we don't want that. We want a minus s to be a negative number. And as long as it's a negative number, then this thing will converge. So in other words, whenever a is less than s, and so now we'll say, okay, if s is bigger than a, then when I take this limit, what do I get?
0.
That
Oh,
entire
no,
thing.
it's 1, and then so just 1 over a minus.
Oh, no. Going to infinity. A minus s is now a negative number.
Oh yeah, so that goes to 0.
And so it does go to 0. This function goes to 0, so we have 1a minus s times big fat 0 minus 1 over a minus s. Okay, so that's 0 minus a minus s. It'll be a little bit sweeter if we write it s minus a. Yeah? And it's the same thing. I could leave it like this. I just like to I don't want to have that negative hanging out there. Okay? So, hold up. What did we just do here? We had a function. We took its Laplace transform. That is, we changed this function into a new function, but now with a new variable, with a variable s. Okay? And let me just get this up here. We took the Laplace transform of the function e to the at, and we got a function out that is a function of s, right?
Yeah.
That function of s is 1 over s minus a.
And a is just a constant.
And a, in this case, yes, a is some constant. And we said, though, for this to work, a has to be less than s. It's whenever s is bigger than a. Okay? Now, earlier, we did the same thing. It's just the case that f of t was 1, right?
Yeah.
Right? Like, we already did that. So we could say that the Laplace transform of the function, the constant function 1, is 1 over s, just so long as s was bigger than 0.
Okay.
Right?
Yeah.
Okay. Here we go. Let's think about graphically kind of what we've done here. Remember, this crazy thing means we're going to take our function, whatever it happens to be, put it in here, integrate it, we integrate it against this kernel, and that gives us a new function now in a new variable, s. Okay, let's think about what we've done here, kind of graphically. Functions, this is a family of functions. E to the at is some family of functions. It looks like this. This is, I'm going to be drawing the family f equals e to the at for different values of a. This is when a is equal to 1. When a is equal to 2, it does that. If a is equal to 0,
Then it's just.
it's a constant function, isn't it? It's just the constant function 1. That's when a is equal to 0. Hey, when a is equal to 0, it's the constant function 1.
Yeah.
Hey, hey, interesting. Okay, now when a, I didn't say anything, there's no problems with a here. A could be a negative number. A could be negative 1. And this is what you get when a is equal to negative 1, and so on and so forth. In fact, we have a family of functions that fills up the entire half plane up here. You can't get anything down here, but you could get everything that's up here, right?
Yeah.
Given any point here, you could find the particular A which goes through that, right there. Okay, okay. So what have we done then? We've taken this, we've transformed this family of functions via the Laplace transform to a new family of functions, which look like this. When A is equal to 1, you have 1 over S minus, so this was my input variable t here. Now we have a new input variable S. And S minus 1, that would take, so 1 over S would be this function here, right?
Yeah.
And it's whenever S is positive, so we can't go back this way. It's only valid when S is positive, so when S is over here, we get this one. This is when A is equal to 0. It happens to be the same thing, right? If A is 0, that's that thing. If A is 0, that's that thing. Right, okay. Now, when A is equal to 1, that takes that picture and shifts him to the right by 1 unit. Over here to 1. And so now we have this function here when A is equal to 1. We'll have another one when A is equal to 2. We'll have this function here when A is equal to 2. Be shifted over to 2. When it's negative 1, you have this function shifted over. Whoop, whoop, whoop. And so that's kind of what the Laplace transform does. It takes functions, a family of functions, and says, okay, we're just going to change you into a new family. But there's this one-to-one correspondence here, right? In fact, you could think about these as being the same function, just in kind of different spaces, right? You could take this function, this constant function, use a Laplace transform on it. Maybe you want to do something over here, do something to it, and then pull it back and see what you get. That's not really where we're going today, but this is graphically what we're doing here. We're taking a family of functions, doing something to it, and ending up with a new family of functions. Okay. We're ready to talk about what nice means. So, okay, I'm going to leave that up there. Nice. Function's nice. And like I said, it just means that the integral converges. So if f is nice, this is the thing. So f has to be piecewise continuous. Otherwise you can't take an integral of it. Like, it could do something like this, and then jump up here, and then do that. And so it's continuous on all of these pieces. And so you can integrate that. You could find the area from here to here, and the area from here to here, and the area from here to here, and then add up all those areas. In other words, it's valid to compute the integral of that thing. Otherwise, you couldn't just plug him in. Because let's get the definition of Laplace transform again. The Laplace transform of f is the integral from 0 to infinity of e to the minus st times whatever f is. And so if you got to be able to integrate it. And as you could take the integral as long as he's piecewise continuous. But we want to know, will this thing converge? Well, here's the condition for it to converge. So a function's nice if it has this property and this property, that the absolute value of f of t is less than some number k times e to the at. For some positive k and some a after t being bigger than some m. Don't worry about this too much. All we're saying here is that you have some function and you could find a k. In other words, we're trying to bound this function. Here's your f, right? and maybe f does something like this, and you want to say, okay, let's look at its absolute value, right? So we're finding the absolute value of f of t and saying, okay, this is the absolute value of f of t. If we could show that there's some k, so that that bounds it, then you could guarantee that that integral is going to converge. Why? Well, because watch this. The integral of e to this, so the Laplace transform of your function is going to be e to the st times f of t dt, which is less than or equal to e to the minus st times the absolute value of it. That's always true. Think back if you need to remember that. And since we're saying, and I think less than or equal to, from 0 to infinity, and that's less than or equal to, by assumption, you found the function that bounds your function. You found a specific k and a specific a, which bounds your function k e to the at, which is the same thing as some big constant e to the minus st e to the at dt, which we just computed is k 1 over s minus a. And so that'll be true whenever s is bigger than a. Okay, so that's what it means to be nice. It means that the integral converges. This is just a way you could guarantee that it does. So as long as the integral converges, then you could take the Laplace transform of it. The Laplace transform is well defined. But who cares? What does this have to do? Stick with me, we'll get there. There's a couple more things that we want to talk about before we get to why we're even talking about this in the first place. First thing is that, I'm going to leave these up here. The Laplace transform is a linear operator. Does that sound familiar?
Yes.
I said before that the derivative is a linear operator. And what we mean by that is that if you have some constant times a function plus some other constant times another function, and you take the derivative of that, it's a constant times the derivative of that function plus a constant times the derivative of that function. And remember, this generalizes, like, because g itself could be another, well, it could be, g itself could be a ch plus d f g h I j k of x, right? And so, you just do it again, right? If g itself, so there's no end to it. All you need to show is that this is true, and then you get infinitely many of them. You know, you remember what I'm saying here?
Yeah.
You see what I'm saying, right? Like, if an operator, and remember an operator in our class is a function whose input and output are functions, right? The derivative takes a function as an input and gives you back a function as an output. The integral takes a function as an input and gives you a function, or a family of functions, as an output. That's what an operator is in our class, right? It's something that takes a function. It's a function which takes a function as an input and gives you back a function as an output. A linear operator has this property right here. That if your function that you're putting into your operator is a constant times a function plus a constant times a function, then the operator is the same thing as the constant times the operator of the function plus constant times the operator of the function. And remember how much easier this made our lives, this property right here? Because, for instance, if we wanted to compute the derivative of, say, 3x cubed plus 2x squared minus 4x, we didn't need to plug this into a difference quotient, right? And try to compute, okay, what's 3x plus h cubed plus 2x plus h squared minus 4x plus h minus 3x cubed plus 2x squared. Because up until this point, up until we proved this, this is what we had to do to take derivatives, right?
Yeah.
And then we said, hey, look, derivatives have this property. So all you need to do, look how easy your life becomes. It's this. You just take the derivative of them individually. Oh boy, that made my life a lot easier. Right. So this is a really nice property to have. An operator that is a linear operator will give you a bunch of goodies that way. My claim is that the Laplace transform is a linear operator, and let's just see. Let's take the Laplace transform of some function that's a constant times a function plus another constant times another function. Well, by definition, you integrate 0 up to infinity of e to the minus st times that thing, which is a f of t plus b g of t dt. But that's the same thing as the integral of e to the minus st a f of t plus e minus st b g of t all dt. But the integral's a linear operator, isn't it? And so, because of that, and this was another nice thing that we had to prove this about integrals, but once we did, we said, whoa, let's make our lives easier. We could just do this. Boom. Yeah? And again, linear operator, pull out the constants. A is a constant. B is a constant. Pull him out. By definition, that is the Laplace transform of f. So that's A times this thing right here is the Laplace transform of f of t. That's a constant, so B times what? Well, B times this thing, which is the Laplace transform of g of t. Right?
Yeah.
And it doesn't end there, because g of t or f of t may themselves have been some linear combination of functions, right? So in other words, like if you had a1 f1 of t plus a2 f2 of t plus a3 f3 of t plus all the way up to an fn of t, you could just keep applying this, right? You do it with the first one, and then whatever this is ends up in your g right here. But then again, now you're just taking the Laplace transform of that. So you peel the next one off, and so on and so forth. And what you end up with is this nifty fact that it's the same thing as this. f1 plus a2 times the Laplace of f2 all the way up to an times the Laplace fn. Everybody believe that?
Yeah.
Have I proved that sufficiently?
Yeah.
Okay, all right, so that's really nice. What can we do with it? Well, hold on. This property, this linear operator property, gives us something really cool right off the bat. Let's say that you took the Laplace transform of some function. Let's say it's y. We'll call it y of t. And so it gave you a function. We'll call it a big capital Y of s. Okay? And let's say that that function of s, instead of being like 1 over s minus a, or something, let's say that it gave us 5s minus 2 over s times s minus 1. So you had some function y. We don't know what y was, but we had this function y. We took the Laplace transform of it, and boom, that guy popped out. Good luck trying to find what y is. Really, good luck. There's a way of doing it. Really hard. Unless you say, wait a minute. The Laplace transform is a linear operator. If I could rewrite this thing as a sum of things times constants, my life's going to be a lot easier. And you look at this and you go, man, that sounds a lot like what I used to do in integrals when I was like, man, if I could rewrite this thing as like, I don't know, an s and then s minus 1. Yeah. In other words, partial fraction decomposition, right? So you do your partial fraction decomposition of this guy, and you will find that your a is equal to 2. Yeah, because I made this up. You see, I started on this side. And that your b is equal to 3. You can check this if you want. Let's make sure. Right? Okay? And so then you go, well, hold up. Wait a minute. So you took the Laplace of some function y, and you got 2 over s plus 3 over s minus 1. And then you say, well, hold up. I wonder if I could think about, because I know that the Laplace is a linear operator, maybe I could think about this. In fact, one more time, I'm just going to rewrite this like this. Try to get this in terms of constants times functions. So now I have this thing in terms of constants times functions, and I'm wondering, can I find a function here, some function f of t, for which its Laplace transform is 1 over s? Can I find some function, I don't know, let's call it g of t, whose Laplace transform is 1 over s minus 1? Can you find anything? Can you find a function whose Laplace transform is this? Is that somewhere on the board, maybe?
Yeah, for 1.
Yeah! If f is equal to 1, then its Laplace transform would be that. And if g is equal to what? We'd have 1 over s minus 1.
If e to the negative t.
Yeah. So let's just see. We said that if f was equal to the constant function 1, and if g of t was equal to what? E to the
positive t.
Positive t, because it's minus a, minus 1, so it would need to be a positive 1, just plain old t, like that. Okay? So, okay, if we could do that, now here's the cool thing about the Laplace operator, is you can say, well, wait a second, the Laplace transform is a linear operator, so we can just keep going and say, wait a second, this is the same thing as the Laplace transform of 2 times f of t plus 3 times g of t, right? That's what that means, yeah?
Yeah.
So then my original function, you've taken the Laplace transform of some function, and you found that this is what it is, so it must be the case that y is this function right here. Yeah?
Yeah.
Right? And you could think about this as saying, like, okay, so we got to this point. We got to this point where we have L of y is equal to L of 2f of t plus 3g of t, which we just found was f of t was 1 and g of t. So this is my y of t. The Laplace of 2 times 1 plus 3 times e to the t, right there. And it's kind of like when you get down to the point where you have like sine x is equal to sine 45, and you go, man, how do I undo that? Well, you take arc sine of both sides. You take the inverse of both sides to get the x by itself. We're trying to get the y by itself, and so we take the inverse of both sides. And indeed, we find the y of t is equal to 2 plus 3 e to the t. And you can go back and check it. Plug that into the definition of Laplace transform, and this is what you'll get. That's what pops out. So, unfortunately, this. So hold up. I don't think we'll need him again, but I'm just going to go ahead and put him here. Okay, and it's Laplace transform. The Laplace of this guy, which is what we started with, was 5s minus 2 over s minus 1. So plug that function into the definition of Laplace transform. This will pop out right there. But of course we didn't know that. We didn't know what this was at the beginning. We started off by saying, well, hold up, let's do this. So it would be nice if there were just some formula for the inverse Laplace transform, right? Like if you could just start here and say, well, why don't I just take the inverse of both sides? And unfortunately, there is a formula for it. Look at it. The inverse Laplace transform of some function y of s is given by, here we go, get ready for it, 1 over 2 pi times I times the limit as t goes to infinity of the integral gamma minus I times t up to gamma plus it of e to the st times that function. It's very symmetric.
That's nice.
In that, like, oh yeah, to undo multiplying by negative e to the negative st, you multiply by the e to the s, but now you get a lot of stuff going on here, and this is, this is a line integral in the complex plane. You have to find the right gamma that works. Like, remember how some of these worked for a certain place?
Is gamma constant, or is it like
Gamma is it's not the Euler-Mascheroni constant.
Okay.
It's just you have to find they use gamma in the literature, but you have to find the one that works in something. But you notice this is not the complex plane, so oh geez, it is not easy to just do this.
Where's the pi?
Take complex analysis. 2 pi pops out everywhere.
Yeah.
Just like,
Sure.
yeah, it pops out everywhere. And
there's
especially...
E's and pi's and i's
Has everything.
It has everything, right? Good luck trying to compute this. But we didn't need to do all that in order to get this, did we? Did we need to do that crazy integral to find out that this thing indeed came from this thing?
No.
No, we used the fact that it was a linear operator, and we broke up our thing into pieces, right? A sum of a bunch of constant times a function, and then just reasoned that, well, since Laplace is a linear operator, if you have some a times L of f plus some b L of g, and that's what your original thing was that you had, well then it must be the case that your original function, since this is L a times f plus b times g, and this is your Laplace transform of your unknown function, then it must be the case that this is your unknown function. And so that's the great thing about this thing being a linear operator, is that we don't need to do the crazy complex variable blah. We just say, well, hold up. If we could get a table of a bunch of these things, and this is what you do. There are tons of tables here that just, like, you could find them anywhere, which on one hand you'll have in the time domain or the t domain and in the s domain. And what this is, it'll give you a function 1, and it'll say that the Laplace transform of it is 1 over s whenever s is bigger than 0. And it'll give you another one. It'll say e to the at, and the Laplace transform of it is 1 over s minus a whenever s is bigger than a. There's a few more that there's tons of them. And t to the n goes over to n factorial over s to the n plus 1, where s is bigger than 0. I'm going to do a couple more. Sine at. The Laplace transform of it is a over s squared plus a squared wherever s is bigger than 0. One more, cosine of some at goes over to s squared plus a squared. Okay, so real quick, here's an example. Let's say you took the Laplace transform of something, and out popped 5 over s squared plus 25 plus s over s squared plus 4.
Yeah, so it's
You could reason here.
sine.
This is the same thing. Yeah, the Laplace of this thing plus the Laplace of this thing, which is 5 squared plus 25, which is s over s squared plus 4. So what would that have to be?
Sine of 5t.
Yeah, so that must be the... Wait. You took the... Yeah, I'm sorry, I shouldn't have done it. We're not taking the Laplace of this. We're saying, here's this thing.
Yeah.
And if you take the Laplace of sine of AT, or sine of what was it?
5t.
5t, so sine of 5t, then that's the thing that you get. We said if you take the Laplace of what thing?
Cosine of 2t.
There you go, cosine, because if that's a 4, then the a squared means that the a needs to be a 2, cosine 2t. That's the same thing as your Laplace of y, which means thankfully this thing is a linear operator, otherwise none of this would be possible. Cosine 2t. That is your thing. And therefore, y must be equal to sine 5t plus cosine of 2t. And indeed, you could check. Use that thing. Take the Laplace transform of it, and that's going to pop out. Okay? Why do we care? Like, I mean, okay. We thought, this is what you do to this function. Great. Who cares? Well, check this out. This is where it gets really cool. What do I want to keep up there? I think I really only just want to keep those up there. And so this is like what you do. There's tables and tables and tables and tables of Laplace transforms, and you could use that to do this kind of stuff. Now, here we go. This is the payoff right here. Did I want to use y? No, I wanted to use f. Let's use f of t. By definition, the Laplace transform of a function is the integral 0 up to infinity of e to the minus st times the function itself. Now let's see what happens if we take the Laplace transform of a derivative. Let's say, well, just by definition, the derivative itself is a function. So I'll just plug in here, right there. That's just the definition of the Laplace transform. E to the minus st times f prime of t dt. Okay. Watch this. I see a product in my integral. One of the things is a derivative. So I'm going to integrate by parts.
Oh,
Du is, let's see, what's the derivative of u? Negative s, e to the minus st. Now, dv, I'm going to choose to be all that other stuff. F prime of t dt.
So v is just f.
And so v is just f. Okay, well, why would I do that? Well, I have no idea what I'm doing. I have no idea. I just saw that there's a product. One of the things is a derivative. Okay, well, let's just see what happens. So uv minus the integral of v du. So uv is e to the minus st f of t evaluated up at infinity and down at 0 minus the integral of, over the same domain, v du. Okay, v is f of t, du is e to the minus st. That minus s can come out, right?
Yeah.
The minus s can come out, so he comes out as a negative s, making him positive. Plug in infinity, and what do we get?
Well, it depends on this. So we have to
We're
assume
assuming
that,
that the s is going to be okay. So right now we're assuming
yeah, this is positive.
s is a positive number. Okay, we're going to assume s is, and if it is, then, and this is another thing about this, is that this thing has to kill him off. Which he will, remember, because we said that in order for this to work, he has to be less than k e sub at. So he's not going to grow faster than any of these guys. He's going to go to 0. So in the limit, he goes to 0. Minus, plug in a 0, I get e to the 0 f of 0.
It's just f of 0.
So plus s times the integral from 0 to infinity e to the minus st f of t dt.
Yeah. Oh.
That's the original Laplace transform. So negative f of 0 plus s times the Laplace transform of your original function.
Okay.
Oh. Watch this. And you're like, okay, that's cool. Same way when I said this is a linear operator, you're like, oh, who cares? And I remember we're in my old house, and you guys are like, okay, real cool name. And then we got so much out of it, you know. I was like, now watch what we can do. We don't need to use a difference equation anymore. And I'm like, oh wow, that's really cool. Watch what's about to happen. I just found out that the Laplace transform of a derivative is equal to s times the Laplace transform of the original function minus its initial value.
Yeah.
Watch this!
Now we don't need to do all of what we just did anymore.
Watch this. Now let's see what happens. Now I'm going to drop this of t stuff in here. That's just annoying. You know it's a function of t. Okay, so now the Laplace transform of the second derivative, well, again, this is just a function. There is nothing special going on. This is a function, that's its derivative. So if that's its derivative, then the original function must have been, I guess, the first derivative minus the first derivative. That's 0. Right?
Yeah.
Right? I mean, there's nothing special. F itself might have been the nth derivative of some other function. Right? So this is, I'm just restating this. I've changed nothing by this, really. Now we could say, but knowing that that's a derivative, this itself, that itself is that thing, which is s times the Laplace of f minus f at 0, which is, let's see, s squared times the Laplace of the original function minus s times the initial value of the function minus the initial condition on its first derivative. Huh. Interesting. So the Laplace transform of a second derivative is in terms of its first derivative, its initial values, and now, now I'm just gonna, we could keep going and keep going and keep going, and what you end up getting is that the nth derivative, s to the n, the Laplace of the original, minus s to the n minus 1 f minus s to the n minus 2 f prime at 0 all the way down to, we'll get the yeah, just so there'll be an s to go along with 1 or 2 before this, so the n minus 2th derivative at 0. And then finally, you'll have no variable attached to the n minus 1th derivative right there.
Yeah.
Right, and you could just do it, and you could make you could do induction on that if you want, but it should be pretty obvious. Now here's the cool thing. This is it. This is it. This is what we're gonna do. And this is the thing. So here we go. Ready? Now this, I'm not gonna rewrite this. This is pretty easy to write. I'm gonna rewrite it. Let's get all of these down. That the Laplace of the first derivative is equal to s times the Laplace of the original minus f0. That the Laplace of the second derivative is equal to s squared, Laplace of the original, minus s f of the original minus f prime at 0. There we go. Okay. Ready? Are you ready?
Yes.
Okay. Now it's interesting, a lot of integral transforms have this really nifty property of like recursion when you look at their derivatives. You take an integral transform of a derivative and you get some kind of formula in terms of the original thing. That is very useful, because let me show you why. Here we go. Y double prime minus y prime minus 2y equals 0, where y of 0 equals 1 and y prime of 0 equals 0. I'm going to take the Laplace transform of both sides. So, the Laplace of this thing and the Laplace of that thing. What's the Laplace transform of 0?
Which is 0. No, okay.
Yeah, because this is just the integral of 0, which is just the flat line. What's the area under that flat line? Well, it's on the x-axis, so it's 0. So, okay, nice. Okay, so that's 0. The Laplace transform's a linear operator. Oh, nice. So, L y double prime minus the Laplace of y prime minus, I'm going to do it this way, Laplace of 2y. But it's a linear operator, so we can pull out the 2, right?
Yeah.
Just like with a derivative or an integral.
Yeah.
That's cool. So, okay. The Laplace of the first derivative is, so So I'm going to start working backwards here. It'll look better. The Laplace of y times 2. There's a minus in front of it. Now, this bit is the same thing as s times the Laplace of the original, which is just y, minus f at 0. There was a minus in front of all of that. This is a Laplace of a second derivative, which luckily we have a nifty form for. So that's going to be s squared, the Laplace of y, minus s f0, minus s times f0, minus f prime at 0. Okay. What might be useful right now is to rewrite the Laplace of y as just big capital Y. Okay. So the Laplace of some function y is, yes, it's a big Y of s, it's a big Y, but right now I'm just going to call it big Y, because it'll make my life just slightly easier. So now we have s squared y minus s f0 minus f prime at 0. Now he's going to distribute in and give me minus s big Y plus, plus f at 0. Now that's just minus 2 big Y of 0. So if I could get y all by itself, right, maybe I'll be able to break it down. Same way we did before, right? We said you had some y of s, and it was equal to 5s minus 2 over s times s minus 1, right? That's what we're going to get right now. We're going to try to isolate the big Y to get y as a function of s, and hopefully we could make everything work, okay? All right, so that's what we're doing. So let's keep all the y's on this side. That gives me s squared capital Y minus sy minus 2y. Let's get everybody else over on the other side. We have s f0. He comes over as a positive s times f0, right? He comes over as a positive f prime at 0. He's already over there. He comes over as a minus f0. Now what's nice is this is an initial value problem. I'm going to go ahead and just plug these guys in. I was using f's, not y's. Why? You know, I'm sorry. I changed notation.
Yes.
Right?
Yeah.
F should have been y. I mean, I even did it right here, right? It should be y that whole time. This should have been. I got it. It's going to drive me nuts if I don't do this. I'm sorry. That should have been this the whole time. I changed because I was copying what I saw over here. Shouldn't have done that. Okay, so y0 is given. It's 1. So that's just s. Y prime at 0 is given. It's 0. y0 again is 1, so s minus 1. I can pull that y out. Pull out the y, and I have s squared minus s minus 2.
And that's just s plus y is minus 2.
S minus 1 over s squared minus s minus
And that's
2.
why it's cancels.
Oh,
because it's minus 2, right?
Because, okay, now let's think about this.
S minus 2 times s plus 1.
Yeah, look familiar. Remember when then we had r's instead of s's, but that's interesting. So, okay, that's the same thing as s minus 1 over
S plus 1 times
Yeah.
s minus 2.
s plus 1 s minus 2. Okay, so let's keep going. Let's partial fraction this guy, because right now I look on my table and I don't see anything that works on my table. So I'm going to partial fraction this guy and say, okay, this is some a over s plus 1 plus some b s minus 2. Okay, so hold up. This is the thing I'm working on. I'm going to clear the denominators by multiplying everything by s plus 1, s minus 2. So that gives me an s minus 1 equals, I'll do it over here, it kills that one and gives me an s minus 2. I do that over here, and that gives me an s plus 1, right?
You can just choose 2 and negative 1.
Let's do 2 and negative 1. I plug in a 2, and what do I get? This guy goes away.
So 1.
Plug in a 2, I get b times 3. Over on this side, I get a 1. So b equals what?
1/3.
B equals 1/3. Now let's do it again with a different value. What did we want to do?
-1.
Negative 1. So negative 1 here makes that a 0. Negative 1 here makes that a negative 2. Negative 1 here makes that a negative 3. So A equals
2/3. Yeah.
A equals 2/3. So, okay. So, hold up. That means that y of s is equal to A was 2/3 s plus 1. B is 1/3 s minus 2. And now we're saying, now if we could find, let's see, because a Laplace transform is a linear operator, what if we could find an f? Because remember, big capital Y of s is my Laplace transform of my original function y. Right there, that's what that was. So, if I could find an f plus 1/3 Laplace of some other function g. So can I find a f where the Laplace of f gives me 1 over s plus 1?
Yeah,
F
e
of
to the
s.
negative t, I guess. Yeah.
E to the negative t will do it. Yes, e to the negative t will do it. Now what about g?
G was so e to the 2t.
E to the, yeah, because, yeah, but, and I want to be explicit here because I don't want to mess this up. The last thing I'm going to do this year, I don't want to mess this up. We're saying that the Laplace of g gave me 1 over s minus 2. The Laplace of g is 1 over s minus 2, so the a would have to be 2. So I want a positive 2 in there. So 2t. Okay, so coming back up here, I'm just going to rewrite what I just wrote, which was that the Laplace of y I was able to write as 2/3 the Laplace of f plus 1/3 the Laplace of g. That's what I had down there. And because the Laplace transform is a linear operator, I could say, okay, then the Laplace of y is equal to the Laplace of 2/3 f of t plus 1/3 g of t. And we found that the functions that do that were that f of t is e to the negative t. So 2/3 e to the negative t plus 1/3 g of t was e to the 2t. And so the Laplace of y of t gave me that. It's the same thing as taking the Laplace of this. Therefore, y of t is going to have to be 2/3 e to the minus t plus
So we found the term.
1/3 e to the 2t, which was the particular solution to our initial value problem. That's pretty cool. I think that's pretty cool. So this is the, like, this whole all morning is like, why do we care about this Laplace transform? This is why, and this is something that you'll see with integral transforms. So notice what we've done. We've taken a differential equation and we've turned it into a like what did we have? We had like y times s squared plus ys minus 2 equals some other stuff involving s. And it's like we've turned a differential equation into an algebra problem.
Yeah.
So this is what's nice about this, and the Laplace transform in particular is suited for differential equations. Is that you can transform your function over into a different space, over into the S space. You go from the T domain into the S domain, and when you do that, your problem turns into an algebra problem. It's an algebraic problem. You have s squared, s to some power, and blah, 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 and you'll always be able to get your y by itself, your capital Y by itself. And now all you need to, so you do that work over there in S space, and then you invert it, pull it back. This is what integral transforms are all about. Like in one space, it's over here in T space, it's really hard to wrap your head around this unless you happen to know a trick, right? So what you do is you go over into S space, turn your differential equation into a algebra problem, solve for y, and then, no, you got y by itself, pull it back, and now you got your answer right there. Yeah. And this is the case with integral transforms, not just with derivatives and stuff. There are different integral transforms do different things like this, where you're over in T space and things are looking ugly, so you transform into a new space, over into S space, and now your problem becomes easy to handle.